Okay, so we solved the two-body problem for Pluto and Charon, and it works the same way for Earth and the Moon. But one question I had for my students, and other students, was how does the kinetic energy of the Moon compare to the kinetic energy of the Earth? Which one has more? And I said in a reference frame that's fixed on the center of mass of the Earth-Moon system. So you are, say, a spaceship cruising out to one side of the Earth-Moon system, and you're moving along with the center mass of the Earth-Moon system. What do you see as far as like the kinetic energy of the Moon and the Earth? How do they compare? So we want to find what this fraction here is. Is this greater than 1? Is it less than 1? Is it much greater than 1? Much less than 1? Is it equal to 1? What? So again, we're looking at a reference frame where the center of mass is stationary. So because we're moving along with the center of mass as the whole system moves around the sun, so the center of mass is stationary here, and I'm just going to color the Earth in blue. But something to note is that the center of mass of the Earth-Moon system is actually inside the Earth. The Earth is so massive that, compared to the Moon, that the center of mass actually, the distance from the Earth's center to the center of mass is less than the Earth's radius. So the center of mass of the Earth-Moon system is inside the Earth. And so what's going to happen, just as sort of a side note, as this system moves along, you remember with the Pluto-Charon thing, we showed how like when Pluto is down here relative to if this is the center of mass here, this big dot, when Pluto is down here, Charon's going to be way up here. Well, the Earth, when the Moon is way up here, further up than I can show you here, because this is a longer distance, but to scale, but you understand, then the Earth is actually going to be like this. So, and the Earth then will move to over here eventually, and then it'll be up here, but it'll always have this center of mass, swallowed inside it. So what it's going to look like to some outside observer watching the system is that the Moon orbits the center of mass, and the Earth basically just wobbles around a bit. This Earth's center is orbiting the center of mass, but it's always, got the center of mass inside it. So it really just looks like the Earth is wobbling a bit as the Moon, orbits around it. So, but anyway, what we want to find is, let me just get rid of these extra circles because they're annoying. Well, what we want to find is the kinetic energy of the Earth and the Moon and how they compare. If we're observing in this reference frame fixed to the center mass. And this actually is very easy. You don't have to assume any kind of orbital dynamics. You don't have to assume they go in a circle or an ellipse or anything. What you say is, so here is the velocity of the Earth, right? And here is the velocity of the Moon, all right? Just to give you some, some visual reference. So let's just flesh out the formulas for kinetic energy. So 1/2, this is the Moon's kinetic energy, is 1/2 mass of the Moon times the Moon's, times the Moon's speed squared. And then for the Earth, 1/2 mass of the Earth times the Earth's speed squared. Now, obviously looking at this, the one thing you obviously want to get rid of first is you can cancel out your 1/2s. Okay, great. So that's the easy part. Now, what do we know? How can we simplify this? What can we do here to simplify this and make it more obvious which of these is bigger? Well, let's look at the total momentum of the system. So we're in a reference frame where the center of mass is not moving, right? Because we're attached to the center of mass. So velocity of the center of mass in this reference frame equals 0. Well, what's our expression for velocity of the center of mass? It's total momentum divided by total mass. But we're in a reference frame where that equals 0. And since, total mass is not 0, well, if it was, we'd have an undefined fraction here and we'd be in trouble. But total mass is some positive number, so you can really just multiply both sides of this equation by total mass, and multiplying 0 by anything still gives you 0. So what you get then is that total momentum equals 0. And so, well, let's just plug in things for that. So this is the Earth's momentum, mass of the Earth times velocity of the Earth, right? This is the Moon's momentum, mass of the Moon times velocity of the Moon, and that equals 0. which then, means mass of the Earth times velocity of the Earth. So the Earth's momentum and the moon's momentum are, the negatives of, oh, sorry, that's an M there, are negatives of each other. So what does it mean when you have, well, that, I guess that should be a capital M since I'm using that for moon, but you get the idea. So what does it mean when one vector quantity, because momentum is a vector quantity, what does it mean when one vector quantity is the negative of another? It means they have equal magazines. Wow. Equal magnitudes, but opposite directions, right? So like these two are negatives of each other, but they have equal magnitudes, they're just going the opposite direction. What this means then is if we want to just take the magnitudes of these, they must have the same magnitudes. So what's the magnitude of Earth's mass times Earth's velocity? Well, it's just Earth's mass times Earth's speed. Easy enough, right? And then the magnitude of the moon's momentum is just, whoops, sorry. There we go. So means the magnitudes are equal. So now we take this, we look up here. Well, this is MMVM, and this is MEVE. These are equal, right? Up here, you've got something that's almost like that. So actually, what we can do is, instead of doing MV squared, we can do something equivalent, which is, let's hope that works. There we go. So this is just the same as MV squared. It's MVV. So I'm just, fleshing out the squares. And now we'll look at this. MEVE is equal to MMVN. Okay? So we take this term here is this here. This here is right here. So the things I've circled in blue, or squared in blue, or whatever you want to call it, are the same. So these cancel out because they're equal. So now we can say that the kinetic energy of the moon divided by the kinetic energy of the Earth is the same as the speed of the moon divided by the speed of the Earth. Well, which one is moving faster between moon and Earth? It's the moon. There are a couple different ways to see that. One is to say, look, the Earth makes this little circle. Well, no, let me not do it in blue. Let me do it in purple, I guess. The Earth makes this little circle around the center of mass. The moon makes a huge circle around the center of mass, so big I'm not even going to draw it all, but it goes big circle around the center of mass. They both have the same period, so the moon must be moving a hell of a lot faster, right? Another way to do it is to look at this formula here and say, well, we're going to reverse this a little, and by basically uncross multiplying, we can find that Vm over Ve, so we divide the Ve over, and that's going to equal mass of Earth over mass of moon. So the ratio of their speeds is actually the opposite or the inverse of the ratio of their masses. So let me rewrite this down here to make it neater, but kinetic energy of the moon over kinetic energy of the Earth, and that mail that arrived a minute ago was my fiance telling me we have a spring break plan. So apparently she's planning something we're going to do during spring break. Hooray! Okay, so that was speed of the moon divided by speed of the Earth, and that's equal to mass of the Earth divided by the mass of the moon. And this, we know the moon is much less massive. In fact, we said the mass of the Earth was approximately 81 times the mass of the moon. So this is actually going to be approximately 81, which means the moon has 81 times as much kinetic energy as the Earth. And the nice thing about this result is this applies to any system of two bodies. A useful, well, I don't know how useful it is, but an interesting application of this whole thing is if you look at the solar system, really to like two significant digits, the only significant masses in the solar system are the Sun and Jupiter. And so if you look at the Sun and Jupiter, really Jupiter orbits the Sun, and the Sun wobbles a little bit because of Jupiter. So the Sun and Jupiter both orbit the center of mass of the Sun-Jupiter system. And really it is like that pretty much, and then the rest of the planets are just along for the ride. Okay, so but what's useful to know there is that the Sun has 99.9% of the mass of the solar system, but Jupiter has almost all the kinetic energy of the solar system, because Jupiter has to move a whole lot faster in order to have the same momentum as the Sun. So it's kind of an interesting interesting little application. But there you go. That's how kinetic energies compare for orbiting bodies. And notice this would also apply even if they were orbiting in ellipses, or even if one was just zipping past the other. In a center of mass linked reference frame, this would still hold true, regardless of whether they were orbiting in circles or ellipses or hyperbolas or what have you. So there you go.